Hi everyone. Okay, let's go ahead and get started. So in this video, we're going to learn about derivatives of inverse trig functions. So I'm going to start by reminding you of a number of things, beginning with inverse functions, and then what are inverse trig functions. Okay, so if you recall from algebra, when you learn about when functions are able to even have an inverse, it was because they were called one-to-one functions. So let me just remind you briefly about that. So recall, only one-to-one functions have inverse functions or have inverses. Okay, and why that matters is because think of inverse as like opposite, going backwards. And so one-to-one functions, those were functions that for every one input there was one output, or vice versa. And it also passed the horizontal line test, if that was like a way for you to visualize it or remember it. So I'll say it like this. These functions pass, and I'll just abbreviate it, the horizontal line test. All right, so real quick, just talking about that. If I want to do the opposite, or if I want to go backwards, so let's say I put a number into my function, I get a number out. If I want to go the other way, if I want to start with the output and find the input, it has to be one-to-one to go backwards. Okay, if I plugged in one thing and two numbers came out, or I plugged in two different numbers and I got the same answer, I know I'm kind of going left with it. Hold on, let me show you like this. So this function real quick is not one-to-one, because if I plug in two different numbers, I'm going to get the same output. So I can't go backwards. So one-to-one functions, they don't have this situation happen. For every one output, there was only one input that got you there. And your inverse trig functions are, because what we do with our trig functions is we limit them and we make them one-to-one. So I'll write that all out here so you can remember how that works also. So recall, and these are your 6 inverse trig functions. I'll tell you a little bit about the domain and range of them each. The inverse trig functions. Okay, so on the left here, I'm going to put the function, and then I'm going to put the range and the domain. So the range, if I'm talking about the inverse or opposite, this is what used to be the domain from the original function. And then the domain is what used to be the range, okay, because I'm doing the opposite function. So for cosine inverse, if you remember, cosine, if you think of a cosine wave, it keeps going and going and going. It's not one-to-one unless you only look at a small piece of the cosine wave. And so that's what we do for all 6 of our trig functions. And so the range that we're looking at, which is like our restricted original domain, is from 0 to pi. Okay, so the only numbers that you're going to get out of your cosine inverse function are numbers between 0 and pi. And so the domain is what used to come out of in the cosine function. So remember from trig, try to remember this. When you plugged in any number, any angle or radian value into your cosine function, the only numbers you ever got out from cosine were as big as 1 or as small as -1. So that's the domain here. So from -1 to 1. Okay. I won't draw this in for all of these, but let me just show you what I'm talking about. So your cosine wave, cosine at 0 is 1. Cosine does this kind of thing, and it keeps going. And so this is not one-to-one, but what we do is we only look at a portion of this, and it's this part here. So I say I only look from here to, let's see, right here. And then I kind of ignore all the rest of this. And then that allows me to have a one-to-one function. This would pass the horizontal line test. Okay, so all of this is sort of things from before. This first part was from algebra. This second part is from trig. I know you might not remember all of it, but I'm just sort of trying to remind you, because what we're going to do today in this section is find the derivatives of these inverse trig functions. Okay, so then let's do the other 5. Your sine inverse function, its range is the original domain, but kind of that limited view of it. So from negative pi over 2 to pi over 2. And it happens to have the same domain because originally sine, you're never going to get anything bigger than 1 or less than negative 1 coming out of your sine function. The next is tangent inverse. And your tangent inverse function, the range goes from negative pi over 2 to pi over 2, but with parentheses, meaning we don't actually end up equaling the endpoints ever here. And then the domain is all real numbers. Next is cotangent inverse. So cotangent inverse, the range is from 0 to pi, but you don't equal the endpoints. Very similar to cosine inverse. The difference is there's parentheses because we don't ever equal 0 or pi with cotangent inverse. The domain here is also all real numbers. And then my last 2, secant inverse of x. The range here is going to be, it's going to look like 0 to pi, but I have to cut off the middle, like pi over 2, because that's never actually going to come out of this function. So it looks like this, from 0 to pi over 2, but I sort of jump over pi over 2, and then go to pi. Okay, that's this notation. So this is interval notation, just if this looks familiar to you. This is your union symbol connecting these 2 sets. And so basically it's saying from 0 to pi, but you can't actually ever equal pi over 2. So we sort of jump over that. And then the last one here is cosecant inverse. And so that, the domain here, let me put the domain, it's going to be from negative infinity until negative 1, and then union 1 to infinity. Okay, so this part here, we just jump over this, any numbers between negative 1 and 1. So anything from negative infinity to infinity, but nothing between negative 1 and 1. And let me squeeze in our last one here. So cosecant inverse, the range on that is from negative pi over 2 to pi over 2, like this one, but we jump over 0. So we say at 0, we're going to jump over that, union 0 to pi over 2. Okay, let's see. All right, so we squeeze that in there. You don't have to do a whole lot with this. I just sort of wanted to remind you about this fact about what you can actually plug in to your inverse trig functions. This is what can plug in. This is what comes out. So these are the numbers that come out of these inverse trig functions. These are the numbers that you can plug in. It's the same domain actually for both of these. So I wrote it once, but it's the same domain there. Okay, so still on the recall part, reminding you of things. The next thing to remind you about is what an inverse function is doing in this situation. Remember I said inverse does opposite. So just sort of pick one. Let's pick sine inverse and think about what it's saying. And you can sort of tell from range and domain where I'm going with this. So recall that if you have y equals sine inverse of x, what does that actually mean? I kind of gave you all the technical stuff here, domain and range. But that means, and you can do it like this, you can actually apply sine to both sides of this equation. So if I apply sine to both sides of this equation, look what happens. On the left, I just have sine of y. And on the right, an inverse composed of its opposite or the original composed of the inverse. Whenever you do this and you take the original of the inverse, or if you did it the other way, the inverse of the original, they undo each other. They're opposites, sort of like square rooting something squared. So this undoes itself and all you're left with is x. All right, so what this is saying is sine of what angle gives me x? So back here, the answer is the angle. And that's the range values here that we talked about. So your answer for all your inverse trig functions is the angle that gives you whatever numbers right here, whatever output is here. So you can try a couple. For example, let's just do one real quick. Let's see if you know this one. Y equals sine inverse of, let's pick square root 2 over 2. That one might sound or look familiar. So this is asking you what angle, when you plug it into your sine function, gives you an output of square root 2 over 2. And the answer there is going to be pi over 4. So just sort of reminding you how this works. All right, the last thing to recall before we can get into all the derivatives is something that we learned recently, which is called the inverse function theorem. So I'm going to tie this all in together, and we're going to end up using this theorem to find one of our derivatives here today. So recall, and this is the inverse function theorem, and we're going to end up using this fact, this theorem. So this says, and this was from just the previous section, if I want to find the derivative of an inverse function, okay, so notice my notation. And remember, math is like a language, a notation language. So yes, I just wrote this symbol on the board, but think about what it's saying to you. It's saying, here's an inverse function. The original function was f, and I want the derivative of it. Okay, so the derivative of an inverse function can be found using the following. You can actually do 1 over the original function's derivative, okay, if you plug in the inverse function into that. All right, so let me say that one more time, and then we'll use this fact. If I want the derivative of the inverse function, I can actually go back to the original function, find that derivative, plug in my inverse function, and then do 1 over that, and that's the answer. Okay, so we're going to use this to find 1 out of the 6 inverse trig function derivatives, and then I'll just list the other 5 for you. So we are going to find the derivative of y equals sine inverse of x. So the derivative of y equals sine inverse of x. Okay, now notice what we need in order to use this theorem. I'm going to say it and then we'll go find it. In order to use this theorem, I'm starting with an inverse function. But this theorem says I need the original. Okay, so I need to kind of take a look at that and write it down. So I need the original. If this is my inverse function, that means the original, and I'll just call it f. My original, f, you can call it like f of x or f of u. I think I called it u just to not get my letters mixed up, like x in the future when I plug in. My original must have been sine. I'll just call it sine of u. Okay, if I'm given sine inverse, the original is sine. What I also need for this theorem is the derivative of the original. So the derivative of sine is cosine. So cosine of u. So I need those two things, and I'm going to plug them into my theorem right here, into this formula that we have. Okay, so let's write that out. And so we have, okay, I'll leave this here, but I'm going to fill in what we're working with. We're working with sine inverse. So we have sine inverse of x, and we want the derivative of it. Okay, so that is our left side. That's this right here. So according to this theorem, this is 1 over the original function's derivative. So this is going to be 1 over cosine. But notice what I have to put. It's cosine of the inverse. So let me put it in another color so you can see it. So according to this theorem, I have to plug in my inverse function into the derivative of my original function. That was this part here. So cosine, I have to plug in my inverse function, which was sine inverse. Okay, so we used our theorem. Now, that's the answer, but it doesn't look so nice. So this is the derivative of sine inverse of x, but let's make it look better. So I'm going to say it like this. Can we rewrite this without sine inverse? Okay. So I want to rewrite this so that I don't have sine inverse in my answer. And this part, we're just going to do a little bit of, use a little bit of trig identities that we know. Okay, so we used our inverse function theorem. We wanted the derivative of an inverse function. It required that we found the original function and its derivative. And then when we found that, we have to then plug in our inverse function into that function. Okay. All right, so from trig, we know a lot of identities, but there's one that comes up often, and it's the Pythagorean identity. So cosine squared u plus sine squared u equals 1. Now I'm going to use this to make this look better, this answer that we came up with. So from our Pythagorean identity, let's go ahead and solve for cosine of u. So if I subtract sine of u, I'm going to get cosine squared u equals 1 minus sine squared u. And then if I take the square root of both sides, technically there's a plus and minus when you do that, you're going to get cosine u, and I'm just going to keep the positive one of this, okay? And I get square root of 1 minus sine squared u. Okay. Now, why I'm doing this, if you kind of can tell where this is going to go, this is cosine of something equals the square root. I'm going to be able to now rewrite this answer that I came up with for my derivative, where I have cosine of something in terms of this. So we're going to replace now. So this was sort of our side work. I'll put it in a bubble. Okay. All right, so back to over here. We have 1 over cosine of sine inverse of x. So 1 over, I now know cosine of u, cosine of the something, and I'll put it in another color so you can see it. Cosine of the something equals the square root. So my whole denominator is this square root. So it's 1 minus sine squared of u. Let's put that also in another color. Okay, and so I just have to fill in what I was taking cosine of. So according to my Pythagorean identity, cosine of this something, the something goes right here in the sine squared. In our case, the something was sine inverse of x. So I'm plugging in sine inverse of x. All right, we're almost to the final answer here. Whenever you're dealing with trig functions, what happens is we tend to write it this way where the power goes next to our function, but what we're taking the trig function of, the argument is behind that. So what I'm going to do here is I'm going to rewrite it so it looks more manageable. So this is 1 over square root 1 minus sine of sine inverse of x quantity squared. This is what it's really saying. Okay, so if this helps, you can always do this. Anytime you have a trig function to a power, feel free to put that power way out there because that's really what it's saying. And usually with derivatives and things like that, it helps to move it out. Now, look at what this is. Sine of sine inverse, these undo each other, and you just get x. So here it is, final answer. 1 over square root of 1 minus x squared. And that is our derivative of sine inverse. Okay, so I derived it using our inverse function derivative formula. However, you're not going to have to do this every time. So I'm going to list all 6 derivatives of your inverse trig functions, and you'll see that there's really only like 3 of them. I know I said 6, but the other 3 just have minus signs on them. So you only have to kind of remember 3 definitions and then put a minus sign to get the other 3. So we went through this the long way. You don't have to do this every single time. It was just to show you how to get this. And now let me list all 6 derivatives for you. So we'll leave that there for just a second, and then we'll make our list. And this is your derivatives of your inverse trig functions. So these are the actual derivatives. All right, so we're going to start with the one we just found, sine inverse, and I'm going to say of u, because a lot of the time what's going to happen is you're going to have to use the chain rule. So I'm just going to account for that by saying that u is like a function of x. So this derivative, we just found this, it's 1 over square root 1 minus u squared. But if you have something going on in your argument, then chain rule says times that derivative, so times u prime. All right, that's your first one. And this is when u is between 1 and -1. So what I'm putting over here is sort of like your fine print. It has to be true in order to use your inverse trig functions. Okay, so that's just like my fine print. This is saying u is between -1 and 1, if I put it like that, with the absolute values. All right, let's do cosine inverse. And like I said, there's 6 definitions here for the derivatives, but you're going to see that it really only looks like 3. So cosine inverse, this derivative is the negative of this one. So negative 1 over square root 1 minus u squared times u prime. And then same thing over here. This is when u is between -1 and 1. So exact same definition for the derivative, other than this has a minus sign. Okay, next one. Let's do tangent inverse. The derivative of tangent inverse of u is going to be 1 over 1 plus u squared, and then chain rule times u prime. And then maybe you can take a guess. If I do cotangent inverse of u, that derivative is identical, but I'm going to put a minus sign. So minus 1 over 1 plus u squared times u prime. Okay. And then remember, the u prime is just if you need it. It's for the chain rule if something's going on in this argument. So sometimes you're not even going to see anything back there. The last 2, secant inverse, the derivative of this is going to be 1 over absolute value of u times the square root of u squared minus 1. And then the chain rule, if you need it, times u prime. This one has our fine print. Absolute value of u is greater than 1. And then the last answer, same thing here, but with a minus sign. So cosecant's derivative, cosecant inverse derivative, is the same one with a minus sign. So let's see if we can make sure you get that in here. So this is -1 over, let's make that more prominent, -1 over square root absolute value, over absolute value of u, square root u squared minus 1 times u prime. Okay, and then same fine print, absolute value of u is greater than 1. So there's your 6 derivatives of your inverse trig functions. We're going to go through some examples now, but just to say it one more time, you really only have to remember 3 things, because sine and cosine inverse, the derivatives only differ by a minus sign. Tangent and cotangent inverse, the derivatives only differ by a minus sign. Same thing with secant and cosecant inverse. The derivatives, the only difference is a minus sign. So you just have to remember like the format, and then we've seen this with the derivatives of regular trig functions. Anything that started with the letter C, the derivative was negative. Same thing's happening here. Cosine, cotangent, cosecant, inverse, all of those derivatives had a minus sign. So it's sort of a quick way to remember which ones have the negative. Okay, now that we know this, you can reference this. So have this available to reference, and then let's try it out. let's find the derivative of one of these. I'll just leave these here for just a second, except for the first one. And we will try this. We are going to find the derivative given y equals cosine inverse of 2x to the 7th. So we're finding the derivative with respect to x. Okay, so we have what the formatting of our derivative looks like, and we're just filling it in basically. So our argument here is 2x to the 7th. So where there's a u, I'm putting a 2x to the 7th. So my derivative, dy dx, is -1 over square root of 1 minus my argument squared times the derivative of the argument. So let me just put it in blue to make it clear. So 1 minus 2x to the 7th quantity squared, and then chain rule times that derivative. And then let's just make this look a little bit better. Notice it just looks exactly like what I have right here. I'm about to erase it, but it looks just like this. I just filled in the fact that our argument was 2x to the 7th. Okay, and so making this just look a little better for our final answer. This derivative here, using your power rule, bring down the 7, it's going to be 14. So on the top, -14. And then your new power is to the 6th, so x to the 6th. Over, and there's not much we can do on bottom other than make that simplified slightly inside our square root. So over square root 1 minus 4, because we're squaring the 2. And then remember your rules of exponents. You multiply these exponents. So x to the 14th. And that is our final answer. That's our derivative. So once we have these inverse trig function derivatives like this listed out, we can kind of just fill stuff in. So let's try another one. Okay, let's see. We're going to do y equals cosecant inverse of e to the 11t power. And we're finding the derivative of y with respect to t. Okay, so we go to our derivatives of our inverse trig functions, and we look for cosecant inverse. And eventually you'll probably start to remember them. But for now, we just learned them, so just sort of reference what we wrote down. We look at what we wrote down for cosecant inverse and its derivative. Okay, so we have that this is going to be the derivative of y with respect to t, -1 over, this one had the absolute value of u, so absolute value of your argument. In this case, it's e to the 11t times square root of, it was u squared minus 1. So that's going to be our argument squared minus 1. So e to the 11t squared minus 1. And then times the chain rule part of this, the derivative of the inside. So the derivative of e to the 11t. Okay, so our format is there, our setup is there. We just have to simplify this. Technically, I haven't finished finding the derivative yet because there's still this derivative right here from the chain rule. So I have to find that and then simplify. So let's go here first. What I want you to actually know is, so e is just a number. It's a natural number. So it's about 2.7 roughly. This is never going to be negative no matter what number you plug in for t. So you don't really need the absolute value bars beyond this point. So I'm going to take them off in the next step. So this is negative something on top. On bottom, I'm going to take off those absolute value bars. So e to the 11t square root. In the inside, again, using your rules of exponents, you're going to multiply these exponents. So this is going to be inside the square root, e to the 22t minus 1. Now on top here, what I'm leaving off is this derivative. So remember, e to a power, its derivative is e to that power times the derivative of the power. So chain rule. So the derivative of e to the 11t is e to the 11t. But don't forget chain rule. So times the derivative of 11t. Okay, don't forget that part. So times the derivative of 11t, which is 11. This will be the answer if I couldn't simplify, but let's simplify. We can do one more thing. Notice in this specific problem, we're multiplying on top and bottom, and we have the same factor. So I'm going to go ahead and divide out this e to the 11t on top with the 1 on bottom. Since I'm multiplying, I can just go ahead and divide that out. So my final answer here is going to be negative 11 on top, and then square root of e to the 22t minus 1 on bottom. Okay. All right, so we used our derivative of cosecant inverse. We filled in what our argument was and just accounted for the chain rule. We had the chain rule once, and we actually had it twice because the argument needed the chain rule as well, this e to the 11t. Let's try one more of these. Okay, so we're going to try this last one. So we have, for example, our function y equals natural log of tangent inverse of 5x cubed, and we are finding the derivative of y with respect to x. Okay, so what I want you to notice first of all is with this one, you have your inverse trig function, which you are going to find the derivative of, but it's inside of the natural log function. So you're going to have to use the chain rule on this, and you're actually going to need it a couple of times. So you have to start with the outermost function according to the chain rule, outermost function, find that derivative and work your way in. So my derivative with respect to x, I'm starting with the outermost part, which is natural log. So the derivative of natural log is 1 over its argument. Okay, so the derivative of natural log is 1 over its argument. So I'm keeping its argument. And then chain rule says times the derivative of the argument. So times tangent inverse of 5x cubed prime. Okay. So this part here was from the derivative of natural log. This part is from the chain rule because there was a whole lot going on inside of natural log here. So this part stays in my answer. So what I'm going to do is I'm just going to focus my attention on what I still need to differentiate, which is this part. So now I have to focus on what is the derivative of tangent inverse. So we're going to go back to what we just learned. You can look at your list and you can say, oh, okay, derivative of tangent inverse was 1 over 1 plus the argument squared, and then if you need it, chain rule times the derivative of the argument. So in our case, derivative of tangent inverse is 1 over 1 plus 5x cubed squared times the derivative of 5x cubed. Okay, almost there. Right here, we still need to differentiate this factor. So using your power rule, just bring down the 3, so that's going to be 15x, and then subtract 1 squared. And so put this all together, and then that's your final answer. So what I want you to notice is that tangent inverse right here is in the denominator. This quantity here is also in the denominator. But when we times by this derivative right here, the 15x squared is the only thing really in the numerator. So when I write my final answer, the 15x squared is on top. On bottom is the tangent inverse from the beginning of 5x cubed, and then times this denominator here, which is 1 plus, and I'm going to go ahead and square this. This is going to be 25x to the 6th. And that is our derivative. Okay, so this section is not very long as far as what you need to know. It was really just those 6 definitions of your inverse trig functions. So we're going to end it here. Just take your time with them, fill it in. If you need to, do like I do and use colors for filling in the argument. And just remember, a lot of times you're going to need to account for the chain rule. Okay, so we needed the chain rule, I think, in all the examples I showed you today. All right, so that's it for this one, everyone.